By the way, I wanted to remind you, your chance to join us at this year's Coleman Columbus Race for the Cure, the largest race for the cure in the nation, by the way.
While searching the web for information on controlling a 20x4 I2C liquid crystal display, I came across a forum post requesting help in communicating with and controlling a Philips TV FM tuner. It piqued my interest and I started exploring a little deeper. The tuners are controlled via the I2C interface, and it turns out the tuners are commonplace in a variety of old analog TV tuner PC cards like the ATI All-in-Wonder and Hoppage cards. I started digging through my collection of old computer hardware in the basement and scrounged up a Hoppage WinTV 61381 PCI tuner card equipped with a Temic 4039 FR5 tuner. The 4039 FR5 is a 3-band tuner, high and low VHF, UHF, and FM. Considering there are no longer any analog television broadcasts, the VHF, UHF bands are useless, but all I was interested in was the FM tuner anyway. 15 minutes after bringing my forgotten treasure up from the basement, and after a lot of careful prying and desoldering, I'd successfully divorced the tuner from the card, removed the excess solder from the interface pins, and plugged into a solderless breadboard. Thanks to the wonders of the internet, it didn't take long at all to locate a datasheet for both the Philips and the Temic tuner. I suspect the Temic tuner uses a Philips IC at its core because both devices use the exact same I2C command set. Now, I had no experience with I2C devices, but I figured playing around with the tuner would be a great way to learn. I was unable to find any websites, blogs, or YouTube videos that explained the mysteries of controlling the tuner, and the forum post I mentioned before was the only sample code I could find. The post was almost 3 years old, and it didn't appear the original poster ultimately had any success in controlling the tuner. Undaunted, I connected 5 volts, ground, and the 2 I2C pins from the Arduino to the breadboard, and used Nick Gaiman's wonderful I2C scanner, which there's a link to in the description below, to scan the Buster devices. And what do you know? It recognized the tuner. I was off and running, or so I thought. Partially because of the dearth of sample code, and partially because the datasheet for the tuner was written to be used by people with a far better understanding of electronics than I have, it took me nearly 10 or 12 hours over the course of a week before I finally managed to grasp the basics and program the tuner and successfully tune in and hear a local radio station through a crappy 2-inch speaker that I pried out of an old PC case. Now that I finally had it working, I drug out the trusty soldering iron again and desoldered a stereo 3.5mm jack from the donor card so I could plug the output from the tuner into my PC speaker's input jack and use the speakers as a stereo amp. Once I had it all figured out, I realized the tuner really is ridiculously simple to control. 10 or 15 lines of code at the most is all that's needed to set the tuner band and the desired frequency. And once I had a handle on controlling the tuner, I added buttons to tune the frequency up and down the broadcast band, a mute button, and attached a liquid crystal display so I could see what frequency I was tuning. Still not satisfied, I added an infrared receiver so I could control the tuner via remote. Now in this video I hope to outline the basics of what it takes to control the tuner and demonstrate some of the functionality I added to the project. Now to start, I think a basic explanation of the I2C interface is needed to help explain how the tuner is controlled. Put simply, the I2C interface is a 2-wire bus that uses a standard communication protocol to permit easy control of I2C equipped devices. Devices are divided into 2 categories, masters and servants. The Arduino defaults to being a master, and most peripheral devices like liquid crystal displays, real-time clocks, ultrasonic rangefinders, and the like are servants. Now each servant device has a 7-bit address assigned to it, usually through hardware, that the master device uses to communicate with it. To avoid having two devices on the bus with the same address, most I2C devices allow one of several addresses to be assigned. Instructions for an I2C device are sent down the bus with the device's identifying address and ignored by other devices on the bus with addresses that don't match. This is a gross oversimplification of how the interface functions, but the purpose of this video is to demonstrate how the interface can be used to control an I2C tuner, not to provide a detailed explanation of how the interface works. Now, this project uses two I2C devices, the 4x20 liquid crystal display and the Temic TV FM Tuner. The display I used for the project is a SaneSmart I2C 20x4 model I picked up at Micro Center for about $13, but I've seen them cheaper online from Amazon sellers and on eBay. Now, to drive the display, I used the library written by F and Malpartida. It supports a wide variety of I2C displays. Unfortunately, there's at least 4 different displays available that all look similar but use slightly different display methods for communication. The Malpartida library provides a standard library that will work with most, if not all, of the different displays. You can download the library from the link I'm going to provide in the description below. Now, the LCD library that comes with the Arduino IDE only supports parallel interface displays. You may have to remove the standard library from the IDE to avoid conflicts with the I2C Malpartida library. As I mentioned earlier, the tuner that I utilized for the project is a Temic 4039FR5 tuner that I salvaged from an old PCI TV tuner card at no cost to me. I have seen used cards on eBay identical to the one I had for as little as $8. Now, only 5 of the tuner's 9 pins are used in the project. Pins 9 and 10, which are the I2C pins, SCL and SDA. Pins 16 and 17, which are the right and left stereo outputs. And pin 20, which is 5 volts, powers the tuner. And additionally, the RF shield, the shell of the unit, is ground. The tuner is controlled by a 4-byte message that's received via its I2C interface. The first and second bytes contain the frequency to be tuned, represented as a 16-bit scaling factor. Now, the scaling factor is basically a multiplier. It's applied to the base tuner step in order to select a frequency. The multiplier is calculated by taking the desired frequency in megahertz, adding 10.7. Don't ask me why 10.7. The datasheet just says to add 10.7, and multiplying the result times 20, since there are 20 50 kilohertz steps in 1 megahertz. The resulting 16-bit word is then split into 2 8-bit bytes, a high byte and a low byte. The third byte in the message is a control byte that, among other things, controls selection of the tuner's internal clock, which in turn selects the change in kilohertz between each step of the tuner. And now the FM tuner section uses 50 kilohertz steps. Now, the fourth byte in the message is a control byte that controls which frequency band the tuner is set to, be it VHF, UHF, or FM, controls the mute function, and allows selection of the data that will be output when the tuner responds to a status request. The signal strength of the currently tuned frequency can be read from the tuner as well, by requesting a status byte from the tuner, with the signal strength being represented by bits 6, 5, and 4. As an example, here are the 4 bytes that would be sent to the tuner to set the frequency to 96.3 megahertz. Take the 96.3 megahertz, add the 10.7 that's required, gives you a result of 107.0. Take that 107.0, multiply it times 20, it gives you 2,140, which is 0.85C in hexadecimal. So the first 2 bytes sent would be 00001000, which is 08 hex, and 01011100, which is 5C hex. In the third byte, the 50 kilohertz step is set by setting bits 2 and 3 off. Now the other bits have various default on and off settings for normal operation as outlined in the table here. The complete byte sent would be 1000 1000, which is 88 hex. The FM band gets set in the 4th byte by setting bits 8, 6, and 3 on with all other bits off. The complete byte sent would be 1010 0100, which translates to A4 in hex. So the 4 bytes sent would be hex 08, 5C, 88, A4. Projects wired. Both the LCD and the tuner are connected in parallel to the Arduino's I2C pins, along with 5 volts in ground to each device. Now the left and right stereo outputs from the tuner are connected to a 3.5mm jack, and none of the other pins on the tuner are used. Now note in this diagram the exact pin layout of the liquid crystal isn't represented. Now to connect the LCD, connect SCL from the Arduino to SCL on the LCD, SDA to SDA, plus 5 volts to plus 5 volts, and ground to ground. 4 of the Arduino's I/O pins are used, 3 of them for sensing when the tune up, tune down, and mute buttons are pressed, and the other to read input from the infrared receiver. I've prepared 2 programming examples. This is the first of the 2. It's a very basic, minimal. This is what's needed to communicate with the tuner. It includes 2 libraries, the I2C wire library and the liquid crystal library to display text on the liquid crystal. I've declared 4 bytes here. Those are the 4 bytes that will be sent to the tuner. I've used default values that are identical to the example I provided. Here I have established 4 bytes that were custom characters that are going to be displayed on the display. Basically, the program initializes the display, creates those 4 characters, and then this send data subroutine down here at the bottom sends the 4 bytes to the tuner, and then displays a little title screen along with the frequency that the tuner was set to. It then goes to this main loop where it just repeatedly asks the tuner for status information and displays the signal strength meter along with a little antenna symbol. It's basically written just to show how simple it is to communicate with the tuner. You see there's not a whole lot to it. Now this is the second of the 2 programs. It's actually a full functioning FM radio. I've included code to allow you to press buttons to tune the frequency up and down or mute the sound, as well as infrared remote functionality where you can adjust the frequency up and down with the remote, as well as choose presets or even define new presets. You can see it uses the same I2C wire library and liquid crystal library, but it now also includes the infrared library. So the liquid crystal library is initialized. There's some pins defined for the infrared receiver, as well as the 3 buttons, the tune up, tune down, and mute buttons, and then a table that stores all of the buttons on the remote and their corresponding hexadecimal codes for the purpose of decoding what button is pressed on the remote. There's those same 4 bytes that are sent to the tuner, as well as a number of other variables used by the mute and tuning buttons and my preset menu routines. Here are those 4 custom characters. That's a little more complicated here. It initiates the infrared library and the liquid crystal display. sends the 4 created characters to the display. Now here we actually read the first preset frequency from the table here, which happens to be the same 96.3. It calls the subroutine to calculate the high and low bytes, which are down here. It takes the preset frequency, calculates the high and low bytes, and returns them. They are then stored in F high and F low, and the send data routine, which is basically the same routine as in the other program, right there, sends those 4 bytes to the tuner and displays the frequency on the liquid crystal display. Now after that's been done, the main loop starts, checks to see if any of the buttons have been pressed. The mute button, if it has been pressed, it mutes or unmutes accordingly. Checks to see if the tune up or tune down buttons have been pressed. In the event it's tune up or tune down, it calls the subroutine called down or up. They're down here at the bottom of the program. There's the one to tune it down. It steps it down by 4 hex, which is 0.2 megahertz, which is the standard difference between one frequency and the next on the FM scale. They go, for example, 96.3, 96.5, 96.7, and this just steps it down in those 0.2 of a megahertz steps. The other routine does just the same, steps it up. And there's extra checks in here to make sure it doesn't go beyond the high end or the low end of the FM frequency range, so you can't tune it beyond where there's any channels to be received. After it checks to see if any of those buttons have been pressed, the program then, if it's not in a mode where it's displaying the preset menu on the liquid crystal display, it shows the signal strength meter down in the corner of the display and looks to see if any buttons have been pressed on the remote, and if they have, responds correspondingly, generates the preset menus, allows you to enter a new preset frequency, allows you to choose from one of the presets that's already there. I'm not going to go into the code. One, it's kind of complicated, and number two, it's kind of sloppily written, and it would take a lot of explaining. Just suffice it to say that this whole section in here checks for each one of the various buttons being pressed on the remote and does the corresponding thing it needs to do depending on what mode it's in, to either set the frequency or choose a preset. And after it's done that, it just loops. I think that's the end of the loop. Yes, it is. Then it loops back up and checks for buttons to have been pressed or for infrared remote signals to have been received. So it just loops through over and over and over again. So although it is more complex, it's all functionality related to the infrared remote and being able to change the frequency up and down. The core part of the program that sets the frequency is still the same. There's still the same 4 bytes being sent to the tuner when the frequency's changed, either by the remote or by pressing the buttons.
See the latest financial position.
I never realized I was back to this till it was too late, and I was hit within. Hurry, feeding on chaos, we're living in sin. Devil, spiral, where do I?